there were some lingering questions about question number 5 in chapter 29, so I thought I'd put together a quick little video to kind of walk you through it. So first let's look at some key points in the example, right? So in the example, we have the frequency of a radio station, we have the power of a radio station, and the key point we want to get down to is what is the power in photons per second. So we start by calculating what is the energy per photon, right? Energy per photon, Planck's constant times F gives us the energy per photon. We want to do this in joule seconds instead of electron volt seconds because we're concerned about the power, which is given to us in joules seconds, and we need our units to match up. It's always important when looking at Planck's constant to choose the one that matches the units for the rest of the problem. All right, so we calculate how much energy is in a single photon, 4.31 times 10 to the minus 28 joules. And then we say, well, that is the photon there's one photon per that much energy. And we know our power is 5,000 joules per second. Well, a photon per that much energy is really 1, right? And we're multiplying by 1 to convert the joules per second to photons per second, right? And this gives us how many photons per second we have in this problem, in this example. Okay, so, and the last piece we're going to need from this is the intensity, right, is power divided by 4 pi r squared. Okay, now these problems diverge at this point. The example and the problem are a little different, right? So we have a 10-watt light bulb, so we're given the power, and we're told that 12% of that falls in the visible range. So in this, we're talking about 12 watts. So I've got 12 watts to be concerned about, right? So my power, right? My power is just 12 watts. Pretty straightforward. Power is 12 watts. Okay, and our photon, well, let me redo that. Our photon, right? Our photon energy we're going to get from, okay, sorry about that. Our photon energy we're going to get from this, right? We have 574 nanometers. So the energy per photon, E gamma above, well, we don't have frequency, we have wavelength. So we use HC, right? HC divided by lambda, right? That gives us the energy of an individual photon, right? And now we've got the power, right? We got the power is 12 watts. We're going to multiply that by 1 photon divided by E gamma, right? And that's going to give us our power in photons per second, right? And we're going to get our power in photons per second, just like was done up above. We've got power in photons per second. Right, so that's all really essentially exactly the same. We have to use HC over lambda instead of HF because we're given the wavelength. We've got to use the fact that we're only using 12% of the power given, so that's 12 watts instead of 100 watts. And now comes the rest of the problem, right? We're asked, how do we get 500, and how far away would we be if 517 photons per second enter the pupil, and the pupil has a diameter of 3 millimeters, right? So first thing we need the area of the pupil, right? Area is going to be pi times the diameter over 2 squared, right? Pi times the diameter over 2 squared. And you're going to make sure, right? You're going to make sure your diameter is in meters. Point in this case 0.03 meters, right? So that's going to give us our area. Now you're asking, well, where do we get everything else? Well, what are we told? we have an intensity, that we have a power, right, in photons per second entering the eye of 517 photons per second. We have an intensity, and this is where we don't know what's going on, intensity right up here. It's power over 4 pi L squared, right? So the power entering the eye is power that you're going to calculate from above in photons per second, right, over 4 pi r squared, right? That's a square, times the area of the pupil, right? That tells us how many photons per second are entering the eye. And we're going to set that equal to our 517, if I could write better, 517 photons, right? I'll just put phot per second, right? So the only thing we don't know in this equation, we know power. We're going to calculate that at above. We know the area. We have everything we need for that. The only thing we don't know is the radius, the distance we are from the light bulb when we get to this power. Okay, that's it for the walkthrough on how to do problem number 5. Good luck, and I'll see you shortly.